Hi everybody, welcome to Lab 12 of your online introductory physics labs. We're going to be looking at the magnetic field of a current carrying wire today. So the goal of today's lab is to examine the radial and the axial magnetic fields of a current carrying coil using a magnetic field sensor. Right? So we're going to look at these coils with a sensor, what this looks like, or what we would expect to see for our radial fields are something like this. So you've probably seen in your class this equation to the left-hand side for a single coil or a collection of coils if you have 2 or 3 or 10 n collection of coils. You're going to have an axial radial field. So in this case, in this drawing, it's along the x-axis. That's the axis of the coil. That looks like mu0, which is our permeability of free space. I is our current. The uppercase R in this case is the radius of that coil. X is how far along from the center. So we call that center x equals 0. X is how far along that axis we're measuring the magnetic field. So we have that relationship. Then also in your class, you might have done the math or been given the equation for a long solenoid. So a long solenoid, the length of the solenoid is considered to be much greater than the diameter here of the solenoid, right? And for that, our axial equation, as long as we're far from the ends, simplifies to mu0 times a lowercase n times I. And that lowercase n just happens to be how many coils per unit length do you have. So if you have like X number of coils per meter of length of this very long solenoid, that's what that lowercase n is. So that's our long solenoid and our single coil. What we expect to see is somewhere in between. So we're going to do a theoretical equation at the end of this lab to try to match our data to an adjusted equation. We're actually going to see that we're pretty close to this coil and a little further away from that long solenoid equation. So here's the experimental setup. As you can see, this is a board that you probably used in lab before we went to all online. And this right here that's wrapped in kind of yellow plastic, that is our coil. So that's not a long solenoid, but it's definitely more than a single coil. So if you look at your lab handout, it actually says that our coil has about 600 turns. So that's our capital N is 600 turns, an average radius of about 1.5 centimeters. So you can imagine as we're coiling this wire, some of the wire is closer to the center, some is further out. There's a certain thickness. So we have to talk about an average radius. And it's got a length of 2.5 centimeters. So neither our first equation for a single coil or a very tightly packed coil or our equation for a really long solenoid is going to quite describe this thing. So that's where we're getting into B theory. The other thing we're using is this magnetic field sensor. So you can see the magnetic field sensor is hanging from a string here. It's in both these pictures, right? And the magnetic field sensor we want to use to look at the axial field, we want to stick to measuring right along that axis. So I want to go straight up and down in the center of that coil. As you can see, we're not quite straight in this one image. So I'm going to take data where I'm trying to hold it perfectly straight and perfectly in the center, but that is definitely a spot where there is room for error, right? So right there where I think I'm on the axis, I might not be exactly on the axis. That's definitely a spot where there's room for error. Now, how we're measuring where we are in space, how we're measuring a position, is that this whole setup, and there's another picture in your lab manual, this whole setup is attached to a string that is over one of the pulleys of the rotational motion sensor. So the rotational motion sensor lets us say where we are in space using the Pasco software. So we're using all of that together to measure both the axial field that we have equations for and a radial field. So we're going to see how different the magnetic field looks on the left side as compared to the right side of the coil from our point of view, let's say. Okay, so our first step in the solenoid procedure is to set everything up in our Pasco software and then take a measurement where I think I am measuring straight up and down the center of my coil. So this right here is straight up and down what I think is the axis of my coil, right? So you can see in here I've measured the minimum magnetic field strength I've measured. The way I had this wired up, I was getting negative magnetic field strengths. That just has to do with the orientation of my sensor and the orientation of the current flowing through this coil. So if you've learned the right-hand rule, you know that if, from our point of view looking down, if current is flowing clockwise, the magnetic field points downwards, and if current is flowing counterclockwise, the magnetic field is going to point upwards. So that's just a function of how I have it wired, right? So this is down through the center of our coil, and then we are asked to go ahead and put the sensor over towards the left side, and you can see over here on the left side, I have a really, really similar measurement for my magnetic field at the center of my coil. And then I'm supposed to do the same thing on the right side. And you can see yet again, I have a really similar measurement. This part right here where the minimum is not quite at my zero position just has to do with me trying to make my best guess of where the center of the coil was and using that as my zero when I started taking measurements. Okay, so then they ask us to measure on the right side with our current reversed. So like I said, if you can picture that you've got current flowing counterclockwise, right? Use your right hand and curl your fingers around in that direction, and you'll notice that with your right hand, your thumb sticks up. So thumb sticking up is telling you that the magnetic field is coming out of the page there, right? You can really, really similarly do the opposite thing where you say, okay, if the current goes clockwise, I can curl my fingers around in my right hand, and to do that, I have to twist my wrist around so that my thumb is pointed down towards the page or in towards the screen if you're watching this on a screen. And I can see that that's the direction of the magnetic field. So this change in sign just has to do with that change of direction of our current, right? But we're still seeing a similar value because I'm still flowing the same current through there. All right. So then we want to talk about axial versus radial directions because we get to this radial field procedure. So it's helpful to look at our sensor here and to look how it works. So our sensor is saying that the X direction that I talked about as being our axial direction is indeed the X direction on our sensor, right? If you can picture, I was dipping the sensor down into the coil of wire, right? This part went into the coil of wire, and I was measuring the axial direction. And if we look at our graphs, you can see that I was graphing the X direction, which is the axial. So our next procedure says we want to look at the radial direction. Well, I write the radial direction in this way on my little image, but on my sensor, you'll notice that I have two other directions here. So I can have a Y direction or a Z direction with this sensor. So I actually want to look at both those directions when I'm looking at the radial direction in this experiment. Okay, so that's what this looks like. I am looking at both the Y and the Z direction. And in this case, I have graphed everything in these two images except for the center run, right? The center was when I was right down the middle of the axis. And we can actually see that we see some fluctuation on the left and on the right in um, our two radial directions. And we can explain that with our right-hand rule and with the way our coil is not like a long solenoid where we're right in the center. So in the center, we see that all those radial things should cancel out. This one's a little funky in the Z direction, but in the Y, it's definitely visible there that they go to zero in the very center. But on the edges, we see that fringing effect. So what that has to do with, if I picture my coil of wire as being something like this, it's almost as round as it is tall. I can picture what my magnetic field lines would look like. So if current, let's give ourselves current heading in this direction, right? I can use my right-hand rule. Again, hold your right hand so that your fingers curl around in the direction that current's going. The way your thumb points is the way your magnetic field would go, right? And so in the center, it should go nice and straight. And so we don't have this radial component, right? Our radial component is sticking out in the radial direction. But as we get towards the sides of this coil, we do see some of that bending. So some of these magnetic field lines, unlike the center line, are going to have a little bending on either end, and that's this radial direction that we're seeing here, is this part of the magnetic field that's bending in either direction. Hopefully that helps make a little sense of this graph. Okay, so then the radial procedure also asks you to look at the center. So you can see the center in both of these, and they should be kind of low. Now in the Z, this isn't very informative. We're only at 18. Remember, our maxes and our mins were at like 210 Gauss. And remember, Gauss is not an SI unit. Gauss is close to an SI unit, though. It's 10 to the minus 4th Teslas, right? It's a more reasonable unit, though. All right. And meanwhile, this guy in the y-axis, we're only seeing a fluctuation from maybe -10 to 10 Gauss. So a pretty small fluctuation. And like I said, that probably has to do with me not staying perfectly on the radial point, right? That radial line of our coil when I was taking measurements. It's a challenging thing to do, we'll say. Right, so those are radial field procedure images. And of course, I'll share these with you on D2L as well. So I said our final thing with our analysis was to do this computation where we're doing a magnetic field model. So your lab actually gives you what you would put in for these different things. We're using our theory for our magnetic field that actually matches with our coil. There's a D distance here that's saying I can adjust where my center point is if I don't feel like I got my minimum there at 0. If I don't feel like I got my sensor zeroed quite correctly, I can adjust that. The radius and the turns in our coil, we're going to leave the same, but we can adjust some of the other items, right, to try to make the model match the theory. So, yeah, the theory match our data, rather. So our theory right here is these red triangles. You can see it's a little narrower than my actual data. So I want to adjust some of these things in the calculator to try to make that match a little better. And I definitely want to zoom in here and match it towards the center per the directions on the lab. Okay, so this is what it looks like when I zoom in, and I did play with the numbers a little bit. You can compare this set of numbers on this slide to the previous slide. I'm actually really pretty happy with how well it matches, really close to the center, but this could have probably been adjusted a little further to match, right? So we can explain maybe why the theory doesn't quite perfectly match with our data and what more we could do there. You can go through the questions in your lab handout and try to answer them using the data that I've given you and your knowledge from your lecture and the couple of terrible drawings I've given you on this explanation as well. Hopefully that helps you guys, and I'll be back next week with yet another lab for you.